You will be surprised to know that there are currently over 12,000 nuclear weapons around the globe. Even more surprising is that Russia alone holds approximately 5,500 of these powerful weapons. They are so powerful that they can cause mass destruction within seconds. But how was it made? It all started in 1789, when German scientist Martin Klaproth discovered a dense metallic element that he named uranium. This discovery increased interest in atomic energy and radiation, which would fascinate scientists for generations. Fast forward to the late 19th century, and here we find the exceptional work of Marie Curie. Through her extensive research on uranium, Curie identified that it was naturally radioactive. That's when she created the term radioactive to explain it. This meant that uranium atoms were disintegrating and emitting electromagnetic particles. Her discovery of radioactivity sent shockwaves through the scientific community and transformed our understanding of atomic science forever. But the surprises didn't stop there. Picking up where Curie left off, British physicist Ernest Rutherford made another astonishing leap in 1911. He suggested that atoms have low-mass electrons that orbit around a dense, charged center called the nucleus. This nucleus holds most of the atom's mass. Rutherford's model was like looking inside the atom and discovering a world more complex and fascinating than anyone had thought. Then, in the 1930s, the scientific world witnessed further advancements. Hungarian-German physicist Leo Szilard conceived the possibility of self-sustaining nuclear fission reactions, or a nuclear chain reaction, in 1933. This concept proposed that the splitting of atomic nuclei could produce enough energy to sustain a series of further splits in other nuclei, leading to a chain reaction. A year later, Italian physicist Enrico Fermi made a big yet initially unrecognized contribution to this field. While conducting experiments with neutrons, Fermi unknowingly caused neutron splitting within uranium. This unintentional breakthrough hinted at the immense potential of nuclear reactions. Taking these insights further, Austrian-Swedish physicist Lise Meitner teamed up with German chemist Otto Hahn to refine the process. Their collaborative efforts led to one of the first successful experiments in uranium fission. Meitner's sharp scientific mind identified and named this revolutionary process nuclear fission. However, the rapidly changing political climate cast a dark shadow over their achievements. The rise of the Nazi Party and its anti-Semitic policies forced Meitner, who was Jewish, to flee Germany. But it wasn't something that would stop her. She continued her work in Sweden, contributing immensely to our understanding of nuclear fission. Her findings became a tipping point in the development of nuclear weapons. But as the world once more moved into war, it was the Germans who held the potential key to nuclear power. While Hahn chose to remain in Germany and continued to develop his research throughout World War II, scientists across Europe steadily fled. Szilard, a Jewish man, migrated to the United States in 1938 to avoid persecution. Fermi and his wife, Laura Capon, also left Europe at the end of 1938 to escape the growing fascism in Italy. Capon, who was also Jewish, traveled with Fermi to New York City, where both applied for permanent residency. As the clouds of war gathered across Europe, the migration of these brilliant minds set the stage for one of the most surprising and transformative chapters in modern history. In the United States, Szilard and Fermi would become key figures in the Manhattan Project. This project was the secret wartime effort to develop nuclear weapons. We will talk about it later in this video. So, the collaboration of scientists was unique. They combined their knowledge and the resources of the United States. Together, they shaped the future of warfare and nuclear energy. The irony was clear. Discoveries first made in European labs ended up in the hands of scientists who fled those countries. Now, here's when things became really exciting. When news of Hahn and Meitner's discovery of fission reached Leo Szilard at his New York City home in early 1939, he wasted no time getting to work. He teamed up with his collaborator, Walter Zinn, and together they recreated Hahn's experiment. This was a massive moment, and Szilard knew it. Reflecting on that night, Szilard shared his apprehensions, saying, "That night there was very little doubt in my mind that the world was headed for grief." Excited yet anxious, Szilard began collaborating with Enrico Fermi to construct a nuclear reactor at Columbia University. They were racing against time, fearing that scientists in Germany who were supporting the Nazi war effort might be developing their own nuclear reactors. In July 1939, Szilard contacted the Jewish-German theoretical physicist Albert Einstein to discuss German advances in nuclear development. This wasn't a casual conversation over tea. It was a mission to prevent a catastrophe that could change the course of history. Szilard and Einstein drafted a letter to US President Franklin D. Roosevelt. The letter, dated August 2, 1939, warned, "This new phenomenon would also lead to the construction of bombs, and it is conceivable, though much less certain, that extremely powerful bombs of a new type may thus be constructed." The gravity of their message couldn't have been more apparent, yet the delivery of the letter faced delays and didn't reach Roosevelt until October. Once Roosevelt understood the potential risks of nuclear weaponry, he wasted no time in assembling a response. He formed the Advisory Committee on Uranium, which held its inaugural meeting on October 21, 1939. But initially, this committee went on pretty slowly, even when the situation was really intense. But when Japan attacked Pearl Harbor on December 7, 1941, it pushed the committee to take some serious steps. Suddenly, what had been a theoretical pursuit became a national priority. The urgency reached a fever pitch after a British report issued in March 1941 confirmed the feasibility of constructing a bomb using uranium. This surprising validation motivated American scientists and policymakers. They knew the atomic bomb would be important for the war effort. However, as their excitement grew, they also realized their resources were limited. This lack of resources pushed committee leaders to ask for military help. They understood that their big project needed more than just science skills. Now, as the United States began its island-hopping campaign in the Pacific, an unexpected player stepped into the spotlight on the home front. It was the Army Corps of Engineers. On August 13, 1942, they initiated the Manhattan Engineer District, famously named after its office location in New York City. Just a month later, on September 17th, Colonel Leslie R. Groves was appointed to lead the project and received a promotion to Brigadier General. Within 2 days, he had made decisive moves to push the project forward by selecting 3 key sites for the atomic bomb's production. One of the first sites Groves chose was Oak Ridge, Tennessee, which was dedicated to uranium enrichment. Another site was Los Alamos, New Mexico, dubbed Project Y. This facility would serve as the weapons research laboratory and the construction site for the atomic bombs. Lastly, Groves picked Hanford, Washington, to produce plutonium from the uranium isotope U-238. Although plutonium didn't occur naturally, scientists found they could produce it within uranium reactors. Its high radioactivity and greater potential for nuclear fission made plutonium an ideal candidate for the bomb. Here's where things became interesting. As Groves made these strategic choices, a secret development in nuclear research was taking place beneath the squash courts at the University of Chicago. Early in 1942, Fermi and Szilard, who had been working to build a reactor at Columbia University, relocated their efforts to Chicago. By December 2nd of that year, they had completed construction. Then they began the methodical process of removing the cadmium control rods from the uranium pile. The climax came when they withdrew the final control rod. The pile went critical, triggering a self-sustaining nuclear reaction that continued to accelerate for several minutes, until Fermi ordered the reactor to shut down. This historic moment produced just enough energy to light a single bulb, but it marked the first time a self-sustaining nuclear reaction had ever been achieved. This incredible success provided nuclear scientists with a template for generating massive amounts of plutonium, which would later become the basis of the B reactor at Hanford. Following formal approval from President Roosevelt on December 28, 1942, the Manhattan Project evolved into an expansive effort that spanned across the United States. Spreading over 30 sites and employing over 100,000 workers, the project ended up costing around $2.2 billion. Despite its massive scale, secrecy was so tight that many individuals involved had no idea of the true purpose behind their work. Encouraged by Fermi's successful experiment in Chicago, scientists realized there were two main ways to make atomic bombs. Number 1, by using uranium, and number 2, by using plutonium. The Manhattan Project decided to explore both methods. This led to the creation of two different types of bombs: Little Boy, which used uranium through a gun method, and Fat Man, which used plutonium through an implosion method. J. Robert Oppenheimer, a physicist from the University of California, led the secret weapons lab at Los Alamos, working on the Manhattan Project. Under his leadership, they developed a plutonium bomb using an implosion method. This was different from the familiar gun method used for uranium bombs. Although testing was expensive and risky, Oppenheimer insisted, and Groves eventually approved a test. Oppenheimer named the test Trinity, after being inspired by a line from a John Donne poem. The test took place at Alamogordo, New Mexico, with a bomb called Gadget containing 13 pounds of plutonium. Hundreds of Manhattan Project workers moved in to prepare the Alamogordo site 200 miles south of the Project Y site. On July 16, 1945, at 5:29 a.m., the bomb was detonated from a 100-foot steel tower. The explosion was much stronger than expected, equal to 21 kilotons of TNT. The blast temporarily blinded the observers, evaporated the steel tower, created a larger crater, and turned sand into radioactive green glass called trinitite. After watching this, Oppenheimer quoted the Bhagavad Gita, saying, "Now I am become death, the destroyer of worlds." So, this is how the atomic bomb was made. This deadly weapon is the result of a massive effort by scientists, military leaders, and government officials during World War II. If you enjoyed the video, make sure to like and share it with your friends. Don't forget to subscribe to our channel for more exciting content.